Okay, guys, welcome. Today we're going to talk about exponential growth, which is an important application of exponential functions. We'll talk about how to describe behavior functions with exponential growth. We'll talk about how to model population growth, and another interesting aspect of this is we can talk about how to compute compound interest. All right, so first of all, what do we mean when we say exponential growth? Well, we say that we have an exponential function that models exponential growth if we have something like c times b to the kx, with the important feature here that c and k are both positive, right? So our usual exponential function is sort of hidden in here. We sort of have the b to the x, but now we've attached a c out front and we've attached a k to the exponent, all right? Now let's go ahead and let's look at an example that we've looked at a bunch of times already. Okay, so we want to look at the graph of 2 to the x on the interval 0 to 8. Okay, so for example, let's look at 0, 1, 2, 3, 4, 5, 6, 7, 8. And we'll see that this sort of gets out of control pretty quickly. And you can imagine that it would do so even more when you have larger numbers there, right? So of course this fits our exponential growth model, because this is just, if we look at it as c times b to the kx, c and k are both 1, which of course is positive, right? So we know that this is going to model exponential growth. Now, if we look at when x is 0, that's 2 to the 0, so that's 1. When x is 1, we get 2, because it's 2 to the first. Then we get 2 squared, so 4. And then 2 to the third is 8. And we're just, to get each next entry, we're just multiplying by 2, right? So that's sort of the idea here. So if I multiply 8 by 2, I get 16, then 32, then 64, then 128, and then 256. All right, so those are just a bunch of powers of 2. Now, what does this look like on a graph? Let's try and draw this a straight line. Okay, it's still not that straight, but it's a little better. Okay, so the idea is that if I go from 1 to 8, 2, 3, 4, 5, 6, 7, 8, my y scale would need to be pretty big to cover all of this, right? So let's just say, let's maybe go by, I don't know, let's go by tens. So this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. So we'll just say this is 130. All right, and we'll get all the points except for the last one. Now, if we plot these points according to our scale here, at 0, we have 1. So remember, this is by 10, so that's going to look something like that. At 1, we have 2, so it went up a little bit. At 2, we have 4, so it's about halfway up there. Then we have 8, it's closer to 10 now. Now we have 16, which is going to be halfway between, well, about halfway between 10 and 20. And then 32 is now a little bit above 30. 64, so 1, 2, 3, 4, 5, 6. Now we're about here. And then 128 is going to be almost at the top here. And then 256 will sort of be off the page, right? So the idea is that your graph is going to sort of look something like this. Okay, so you can see that the graph, after a while, it starts off slow, but then it really starts to pick up steam and really starts to grow fast. And that's sort of the idea behind exponential growth, is that you're going to start off slow, but then really pick up steam. Okay, now, one way that you can think about this is that a function will have exponential growth if you take the logarithm of it, and then you get a line with positive slope, right? And sort of the idea behind that is, so we know that f of x for an exponential function would be something like c times b to the kx. Now, if you take the log of f of x, then we have the log of c times b to the kx. And we can use some of our log rules to break this up, right? So we could say that this is log of c plus log of b to the kx. And then by the power rule, we can bring this down. We have log c plus k times x times log of b. And of course, you can make this into a linear equation, y equals mx plus b. As long as you dress it up a certain way, we would need to say that k times log of b is our m, and then we have x plus log of c as our b. All right. Now, the constant term doesn't affect whether or not, doesn't affect your slope, right? But if this is positive, then your slope is positive, right? So of course that would mean that k would need to be positive and log of b would also need to be positive, right? So that's sort of the idea there. Okay, so as an example of this, we see that we have the observation that computing power has exponential growth, right? Each year we have that our computing power doubles on average every 1.5 to 2 years, right? So if we look at this graph that's displaying the logarithm scale of our computing power, you see that this is roughly aligned with positive slope. Right. So if you have that your logarithm of your exponential growth is a positive sloped line, then of course this will have exponential growth. So the answer to this question, of course, is yes. All right, but that's sort of the idea. Okay. Now, we can of course say that in a little bit of a simpler form, if you can do away with the k, this is basically just setting k equal to 1, which is a positive number. Then we can say in a simpler version, which is sometimes apparent, that exponential growth is also c times b to the x, as long as c is positive and b is greater than 1. Right? So that's another way that we can form an equation for exponential growth. Now, what you can also do to model exponential growth is you can let b just needs to be a number bigger than 1, larger than 1. So of course, if we let b be 2, which is going on here, this also models exponential growth. And this is sometimes used because if you have base 2, then you can talk about how often a quantity doubles, right? And that's an interesting application here. Okay. Now, here's an interesting problem. We're going to use the simpler form. We're going to use f of x is c times b, oops, so I need to do c times b to the x to model my exponential growth. Okay, now here we're given 2 points, right? We're given that 2 comma 3 is a point, and we're also given that 5 comma 7 is a point. So we want to figure out what is a formula that is modeled by this exponential growth, right? So what we would do, well, we need to find c and we need to find b. If we have that when x is 2, that y is 3, then we get that 3 is equal to c times b squared, right? And this equation gives us that 7 is equal to c times b to the 5th. Okay, so now what we have is two logarithmic equations. Okay, so what we can do, for example, is let's solve for c here. So if we solve for c, we could say that c is equal to 7 over b to the 5th. We can now take this and plug it in here to get what our b is. Okay, so if I bring this over here, we'll get that 3 is equal to c, which we just said was 7 over b to the 5th. Right, this is my c. And then I still have b squared from before. Okay, so now we can use our exponent rules to say that this is 7 over b to the 3rd. And now we can solve this for b. If I multiply both sides by b to the 3rd, I'm going to get 3b to the 3rd is 7. So we're going to get that b, once I bring the 3 over and take a cube root, get that b is the cube root of 7 over 3. All right, and now of course we can use this information to get our c term. And if we plug that in here, we get that c is equal to 7 over b, which we just found was the cube root of 7 over 3, all to the 5th power, right? So this is some gross number, and that's totally fine, right? So that's what our c value is here. So what's the function that models this? And could we simplify this a little bit more? Let's see. So we could say that this, for example, is 7 over 3, and then using our exponent rules to the 5 over 3. So we could say that this is 7 over 7 to the 5/3 divided by 3 to the 5/3. And then we could divide by the fraction. We could say this is 7 over, times 3 to the 5 over 3 times 7 to the 5 over 3. And then use our exponent rules. We could say this is 3 to the 5 over 3 over 7 to the 2/3. Right? So I guess what we could finally say is maybe a little bit easier is we could say that this is 3 to the 5th over 7 squared, all to the 1/3. Maybe not that much easier, but that's all right. Okay, but anyway, however way you frame it, that's your c. So we can say that our formula for this exponential growth is c, and I'm just going to use the original one, the 7 over the cube root of 7 over 3 to the 5th times b, which we said was the cube root of 7 over 3 to the x. All right, so it's an ugly model, but that's our model nonetheless. And of course, part B says to find f of 17, and that would just be plug in a 17 for x, so you get a 7 over cube root of 7 over 3 to the 5th times cube root 7 over 3 to the 17th. All right, well, of course, here we can use our exponent rules. We can cancel 5 of these with 5 of these, and we have a 12. So this just would be 7 times, now I'm going to convert this to exponential form because we could say this is 7 over 3 to the 12 over 3, which is 7 times 7 over 3 to the 4th. So we get that this is 7 to the 5th over 3 to the 4th. Let's see what this is in the calculator. So we get a 7 to the 5th, which is a 16,807, and 3 to the 4th, which is an 81. And let's see, if we divide this, do we get something nice? Divided by 81. We don't get something nice, but we get 207.494, roughly. All right, but anyway, that's how we can use sort of 2 points to come up with a exponential growth model. Okay. Now, in this example, we're going to use the sort of the base 2 formula. We're going to use the C, we're going to use this one, the C times 2 to the kx, all right? And the reason why we're going to use that is because they say that we have doubling. All right, I didn't read the problem first, but I sort of saw it and I wanted to make sure I mentioned that. So the model that we're going to use is f of x equals C times 2 to the kx. Okay, now we're supposing that a colony of bacteria in a petri dish has 7 cells at 1 p.m. and the bacteria produce at a rate that leads to doubling every 3 hours. Right, so how many bacteria cells will be in the petri dish at 9 p.m. on the same day? So what we're essentially being told here is that if we have 700 cells at 1 p.m., we could say that when I plug in 1, I get 700. And that's 1 point. And if we know that it doubles every 3 hours, then after 3 hours, which is where that 4 is coming from, taking 1 and adding 3 to it, the population should double. So I should get a 1,400 now. All right, so those are sort of my 2 given points that we could use here. Now, we're going to use the same strategy that we just used before to figure out what our variables have to be, right? So we could say that 700 is equal to C times 2 to the K times X, which is times 1 in this case, right? And then the second equation gives me that 1,400 is equal to C times 2 to the 4K. Okay, so now we can use these equations to solve for the other variables, right? So here, just like before, we could say that 1,400 over C is equal to 2 to the, oh, sorry, no, I want to divide the other term over. Okay, so if I divide by 2 to the 4K, that gives me C. And just like before, I want to take this C and plug it into this equation. So that way I get 700 is equal to 1,400 over 2 to the 4K times 2 to the K. And then by our exponent rules, we're going to get that 700 is equal to 1,400 over 2 to the 3K. All right, now if we cross multiply, if I think of 700 as 700 over 1, I'm going to get 2 to the 3K times 700 is equal to 1,400. And then we can divide, and something nice happens here, because if we divide by 700, we get 2. So I don't even need to convert to a logarithm here, right? This exponent is 1, so we get that 3K is equal to 1, so K is equal to 1/3. All right, so if K is equal to 1/3, I can use that to find C, and I'm going to get that C is equal to 1,400 over 2 times 4 to the 1/3, which is K. So we get that C is equal to 1,400 over 2 to the 4/3. All right, and that's my C value. So we can say that our model is 1,400 over 2 to the 4/3 times 2 to the K, which we said was 1/3, times X. Okay, now we want to use that model to find how many bacteria will be in the petri dish at 9 p.m. So that just means we need to find f of 9. So we have 1,400 2 to the 4 over 3, and then this is going to come 2 to the 1/3 times 9. So we get that this is 1,400 over 2 to the 4/3 times 2 to the 3. And of course, we can use our exponent rules. We can cancel 4/3 of these with 4/3 of these, And we'll get that this is 1400 times 2. And let's see, if I take 3 and I subtract 4 over 3, I should get a 5/3, right? So now this is just something that we'll plug into the calculator. I need to do 1400 times 2 to the 5 over 3. Oops. 5 over 3. And we get that this is roughly equal to 4,444.73. So that's how many bacteria cells we can expect in the colony. All right. Now it turns out that we can model this in a little bit more of an efficient way. Okay. So if our initial population is P0, and we know that the growth doubles, so doubles every D time units. And let's see. I'm sorry. And then T0, so this corresponds to T0. Oh, sorry, at time T0, not T equals 0. All right, which is usually the same thing, but I want to be consistent. Okay. So we can use this model to also show doubling time. All right, so that's an interesting application. Okay, now let's look at another doubling time frame. So we have that the world population in mid-1950 was about 2.56 billion. So in 1950, we have 2.56 billion. Right, and then we are being told that the world population doubled during this time every 40 years. Okay, so we're going to use the model that we just looked at. We're going to use that f of x is equal to p0 times 2 to the t minus t0 over d. All right, well, here we're being told that our doubling time is 40 years, so d is 40. Our initial population that we're working with is 2.56. And to make things easier, we'll set T0 equal to 0 in 1950. Right, just so that we don't have to use our T0 be something like 1950, right? So we're just going to sort of realign this just to make this a little bit easier. So now if we use this information in our formula, then we get that our model could look something like 2.56 times 2 to the t. Now T0 is 0, so I don't need to write that part, over d, which is 40. So that's going to model my population for this time period. Now for part B, we want to use this formula to estimate the population in 1955. All right, well, if we made T0 0 in 1950, then this really corresponds to t equals 5. So then I need to find f of 5, which is 2.56 times 2 to the 5 over 40. So if we enter this in the calculator, so we get a 2.56 times 2 to the, now if you're going to enter this in the calculator, make sure that you put that entire exponent in parentheses or else it won't come out right. But anyway, if we enter that in, we'll get that this is, again, roughly 2.792 billion. All right, so that's a cool problem where we can sort of use doubling time in a realistic scenario that we can sort of all sort of relate to. Okay, now the remainder of this section is going to talk about interest problems, right? So bank bank type of interest problems, right? Now, the first type of interest that we'll talk about is simple interest, right? So this means that no interest is paid on any interest that accumulates. It's only dependent on the initial deposit. So for simple interest, you have that this A, I usually use A, is equal to P times 1 plus RT, right? And of course, what do all of these numbers mean? Well, P is the initial deposit. R is the interest rate as a decimal. T is the number of years that go by. And most of the time, but not all the time, A is what you want to solve for. A is the final amount, or the amount at the end of the T years. All right, so that's sort of the formula that we can use for simple interest. So as an example, we want to suppose that we deposit $8,000 in a bank account that pays 5% interest. We want to assume that the bank pays the interest once per year at the end of the year, and we place the interest in a cookie jar for safekeeping. Okay, so in part A, want to know how much will we have at the end of 2 years. Okay, well, again, we want to use A equals P because it's simple interest, 1 plus RT. And A is the thing that we want to find. So we'll leave that blank for now. Whereas P is what we're starting with, which is the $8,000. Our interest rate was 5%, but as a decimal, I want to write that as 0.05. So if you want to convert a percent to a decimal, you just move your decimal place over 2 spots. And then, of course, T, in this case, the number of years is 2. So I want T to be 2. So with this in mind, I can get A by doing P, which is 8,000, times 1 plus R, so 0.05, times T, which is 2. And that will give me the simple interest after 1 year. So if I do this in the calculator, I'm doing 8,000 times 1 plus 0.05 times 2. And that should give you 8,800. So that would be the amount after 2 years. Now, in part B, we want to come up with something that models the interest after just some number T. So we're going to leave T by itself in this case. So we have A still unsolved for, P is still 8,000, R is still 0.05, but T we're just going to leave as T. So now if we combine this information, we get A is equal to 8,000 times 1 plus R we know is 0.05, but T, of course, we're just leaving as T. So then we can leave it like that. Now, what you can also do is that if you were to distribute this, you're going to get an 8,000 and then 5% of 8,000, which should be a 400. So we get a plus 400T. All right. And what's interesting about presenting it in this form is that this is your original amount. And this represents the interest. So you're getting $400 in interest per year. So that's sort of an interesting way that we can present that answer. Okay, now I'll talk about compound interest. Now, the difference between simple and compound interest is that compound interest also takes into account interest that you've already gained, right? So you're also going to be sort of accumulating additional interest every year rather than just on the initial deposit. And here the formula is a little bit different. You get that A, let me just zoom in. You get that A is equal to P times 1 plus R, and instead of being multiplied by T, this entire quantity is raised to the T power. Okay, so let's do an example of this. Okay, so here we have the same information, it looks like, only now we want to see what happens if this is compound interest. Okay, so in part A, we want to find out for 1 year. And again, this is compound interest, so we're doing P times 1 plus R. to the t power now. So of course, A is what we're trying to find. P is the initial amount, so that's the 8,000. R is the interest rate, so that's 0.05 again. Excuse me. And then here t is equal to 1. So if we plug this in, we get A is equal to 8,000 times 1 plus 0.05 to the first power, right? And of course, if we multiply this out, if we do 8,000 times 1 plus 0.5 to the 1, we're going to get that this is 8,400. And of course, this is no different from the simple interest case because we haven't gotten any interest yet. We're still going to only collect $400 worth of interest. But now in part B, this is where it will start to get different, because now compound interest is going to take into account that you have 8,400 in the account rather than just 8,000. So now when we do the problem, we're doing the same thing, except we're changing this exponent to 2 now. So now if we calculate this, we want to do 8,000 times 1 plus 0.5 to the second. And now here you get 8,820, right? So you're getting an extra you're getting an extra $20 in this case, because now you're accounting for that $400 that's already in there. All right, and then again, part C wants it just after t years, so this is going to be 8,000 times 1 plus 0.5 to the t, right? Or if you want, you could say this is 8,000 times 1.05 to the t, right? You can just add those two together. Okay, so that's the compound interest once per year. Okay, now here's an interesting problem. In 1626, we had that Dutch settlers supposedly purchased the island of Manhattan for $24 from the Native Americans. All right, so determine whether or not this was a bargain or not, we're going to suppose that the interest on this $24 was 7% per year. And we're going to assume that this is compounded once per year since 1626. All right, we want to know how much would this investment be worth in 2017. All right, so again, A is what we're after. We're using the formula A is equal to P, 1 plus R. Now this is compound interest, so it's raised to the T. Now we're starting with $24, so not a lot, of course, right? And R is equal to 0.7%, or sorry, 0.07 because it's 7%. And now T, the number of years, I have to figure out what 2017 minus 1626 is, right? So I'm just going to let the calculator do the work on this. If I do 2017 minus 1626, we get that this is 391. Now, if we plug this in, we get that A is equal to 24, 1 plus 0.07, so 1.07 to the 391. All right. Now let's see what this comes out to be. So if we do 24 times 1.07 to the 391, okay, we get a huge number, right? We get 7.4 times 10 to the 12, right? Which means that you have 7.4, but then move the decimal place to the right 12 times. So you're going to get basically 11 zeros after the 4. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. So it looks like if we put the commas in, we get so let's see, this would be million, this would be billion, and this would be trillion, right? So we're assuming that this $24 after 391 years would grow to $7,400,000,000,000, right? So you could look up how much is the island of Manhattan worth today and see whether or not that's a bargain or not. But that's sort of an interesting problem. Okay, now I believe this is the last type of interest. Yeah, the last type of interest that we're going to look at is the idea of compound per interest, but instead of compounding it once at the end of each year, you're now going to compound it n times per year. So the formula hasn't changed much, but we are including this n value in here now. So we're taking r and we're dividing it by n, and we're also multiplying our exponent by n. And n is just the number of compounds per year. Okay, so if you have like monthly compounding, that would be n is equal to 12 because there are 12 months in a year. If you have yearly compounding, that would be n equals 1. If you have semi-annually compounding, that would be n equals 2. And of course, daily is like 365. Okay, so now in this example, we're looking at the same scenarios before, but now we're saying that we're compounding twice per year. So if we're compounding twice before, that means that, sorry, twice per year, that means n is equal to 2. So when we do our a equals p 1 plus r over n to the nt, because this is multiple compounds per year, well, a is again still what we're trying to figure out. P is still 8,000. R is 0.05. And we said that n was 2. And if we want the end of 1 year, we want t equals 1. So this is a equals 8,000. 1 plus 0.05 over 2 to the 2 times 1. So if we enter this into the calculator, and again, anytime you have an exponent with multiple terms, make sure that that's in parentheses. But we want 8,000 times 1 plus 0.05 divided by 2, and we want to raise that to the 2 times 1, and that's going to give us that we have 8405. So you see that by compounding twice per year, you pick up an extra $5 along the way. Okay, last example that we'll do, and it looks like we have a similar example. So we still have the same starting amount. We're compounding 12 times per year, so that's n is equal to 12. And now we want to know how much is in the account after 3 years. So t is equal to 3. So let's fill in what we know. So again, we're using a equals p times 1 plus r over n to the n times t. A is what we're trying to figure out. P is 8,000. R is 0.05. N, they told us, was 12. And t is equal to 3. So if we combine all this, we get a is equal to 8,000 times 1 plus r 0.05 over n, which is 12, now to the 12 times 3. Okay, so if we enter this into the calculator, we're going to get, so let's see, 12, and then to the 12 times 3, or you could just do 36. And it looks like we're going to get that this is $9,291.78. All right. So in general, it does help to have compounding happen more frequently, right? And that would, of course, increase the amount. All right, but that concludes this video on exponential growth. I hope you enjoyed, and I will see you next time.